And action. Start out with the traditional. Any questions? All right. We last left off, seems like we're doing circular motion stuff. We did car going around curve.
I think so.
Did we actually solve it? I was trying to remember.
No, we just set it up.
We set it up.
Yeah.
We got the equations, or we got the set of the problem? Force diagram?
I think that's as far as we got, yeah.
Force diagram? Okay. And what, did I give numbers?
Just that frictionless.
So some angle theta here as this car goes around the curve. And so the force diagram gets worse and worse the farther down the board I go. Has anybody put one of these boards up before? I was wondering if I could somehow raise it a foot easily. Okay.
I mean, I've put them up, but not one that many.
Oh. Is it, when you put them up, glued on the other side, or?
No, most time it's screws, and then you, it's the way that you hook it on the back.
Are there multiple ways? I mean, if, let me just look. All right, you wanna look from this side?
Yeah.
Easier.
I don't like all your markers. Yeah, this one may be glued. Looks like you got a screw here.
The one I was trouble I get into was like I halfway through it and realized I'd made a mistake.
Couldn't get in too much trouble, just call maintenance and tell them it failed. Another screw here.
Yeah, but then I have to edit this part of the video out.
Another screw here.
That's good, okay,
Yeah, that's what it is, it's screwed in.
okay. Thank you. All right, so the force diagram, we had weight acting down, and we had normal force acting up, or up and to the left. And so the big thing for these problems, and we probably covered it last time, but let's make sure we hit it again, the direction of acceleration. This thing is traveling in a circle. What is the direction of acceleration? Suppose the car were here, what would be the direction of acceleration?
Down,
And here,
to the right,
what is the general rule for something traveling in a circle?
towards the center.
Absolutely. So my acceleration is in that direction. The acceleration is not part of the force diagram. It is just there as a note. So, coordinate system, or coordinate axes. Do we get that far?
I don't think so.
Okay, so what is the coordinate system we should probably pick for this?
One that's parallel and anti-parallel to acceleration.
Ooh. Parallel, I'm good with. Anti-parallel, so parallel would be that way, anti-parallel. Say it again?
Perpendicular.
Yeah, okay, there we go.
Word's not good.
I'll put I hat, J hat. As such, they are perpendicular to each other. So therefore, what needs to be broken up? Under
Normal. Yeah, wow.
Yeah. Weight is not broken up. This is very unlike the box on ramp problem where you're breaking weight up. You are breaking normal force up. And so we need to do a little bit of geometry here. So what I'm gonna do is I'm just gonna draw out my ramp here, my angle theta, and normal force is going this way. That's what I need to break up, and normal force is supposed to be perpendicular, so why don't I actually try and draw it as such? At least that's closer. And so we sort of piece it together bit by bit. I'm gonna draw a little horizontal right there. So if this angle here is theta, what is this angle right here?
Would also be theta.
Say it again, Amy?
Theta.
Yes, indeed. This is a right angle. Again, the normal force is normal to the plane. What is this angle right here?
Yeah, here.
And let me get the door.
Wasn't that one theta also?
90 subtract.
Yeah, 90 subtract theta. It's the complement.
Is that, yeah, that.
Is that what you meant?
I couldn't remember what you called it.
Oh. The complement, or I generally call it theta prime.
Yeah,
Did you say prime?
no,
Oh, okay.
that's what I wanted to say, but again, I didn't remember.
No problem, we're there now. So I'm breaking up this lovely vector here into perpendicular components. So one part that is in the direction of I and the other part in the direction of J. Those are my parts. This angle up here has to be theta, because it's the right angle there. And so my horizontal piece here is opposite theta. And which trig function is associated with opposite?
Sine.
And so I now have weight acting down. To the left, I'll have y times the sine of theta, and then up, I'll have y times the cosine of theta. And once again, sine of theta is in the direction of acceleration. The other way of doing it is, again, whenever I draw my ramps, they almost always look like 45-degree angles. I could also have just drawn it a skinny angle like that. Got my normal force perpendicular to it when I'm breaking it up. Yeah. If that angle is small, well, the opposite side is going to be the small one. So that's going to be sine, because that's the small one. Or you type into your calculator sine of angle and cosine of angle, and the smaller of the two is associated with the smaller side, and the larger of the two is associated with the larger of the two. All right, so force diagram, direction of acceleration, coordinate axes, decomposition, equations of motion. How many equations of motion will there be? In unison.
30.
Sounded like a single voice. That was really good, class. Sorry, Amy, you said,
I said 3.
why 3?
Because of your coordinates that you set up earlier. No. Yeah,
Because I have 3 forces here.
yeah. So
Remember, the forces that are parallel or anti-parallel will show up in the same equation,
just 2.
is indeed 2. My model, F equals ma. And that's pretty much going to be the model until we get to chapter 9, and then we're going to do a variation of that, tau equals I alpha, but that's for future us. So we'll have 2 equations. Another way of looking at it is the fact that I have one coordinate system set up here, and there's just 2 sides here. There's just an I and J. I don't have a K involved. So somebody bravely, proudly, give me one of the equations. Take chances. Now, I see some people looking stuff up, that's fine, we'll give people, oh, James.
J hat is gonna be y cosine minus w equals 0.
Boom, one done. It's the J hat equation. We'll stick a little J hat over here. And I do want to sort of bring up the fact that this is an equation, so an equation I am expecting an equal sign here. So the force is equal to mass times acceleration. Sometimes people will just write J hat equals, and which is inappropriate. J hat is a unit vector, these are not vectors here. These are just the magnitudes in the J hat direction. All right, the other one, someone proudly, go for it. And go for it.
Y sine theta equals ma.
There's the I hat equation. Thank you, James. Now, the people who were hesitant, is it the fact that you just have so little confidence, you're an introvert, or?
For me, I just have a hard time trying to remember what like goes together, I guess, in the equation.
Is it the forces equals mass times acceleration, using, being able to apply the template, or the fact that why these two go together?
Why those two go together?
Okay.
Yeah.
Yeah, I'm not quite sure what else to do other than, they're, but
That's essentially it though, if they're in the same line, then they go together.
yeah, absolutely, that's it.
Okay.
Thank you, Brandon, for speaking up there. Anyone else want to offer what I guess if you're an introvert, then,
I just don't like speaking out.
oh, okay.
No, I'm with him. I just don't know what goes together sometimes.
But the fact, but at this moment, are you good with the fact that the stuff that
Yeah.
is in a line goes together?
Yeah.
Okay. And I want to just sort of put a slight twist on it. I've got basically an object right here. If I had written it as y cosine theta going up like that, and then w going down like that, this would still be considered in a line, even though I didn't draw them perfectly lined up.
Right.
Okay. Didn't want that to mess you up. All right, so we have my two equations. What comes next? And thank you, Jacob, also for speaking up.
Simplify? Simplify?
One step before that. In some sense, make it more complicated, but
Substitution.
that's the one. Woohoo!
Bunch of carrots.
All right, thank you. She's my food dealer. All right, substitution. For what do we have a formula that is independent of this problem? And I will tell you, we have a formula independent of this for two things here.
Acceleration.
That's one of them. We have a substitute problem for acceleration, and the other one?
Weight, I think.
Yeah.
Yeah, weight.
Yes. Drop the I think. You know. Wait. Now, I'm hoping if you're not there right now, because your mind's just not lubricated yet, that it will, very shortly, you will go, oh, of course. What is the formula for weight? Without looking at your notes. In unison, that'd be awesome.
MG.
There we go, sounded like a single voice again. That's how good you guys are. But it also sounded unidirectional, so that kind of strange. The ventriloquist we have, it's amazing. Y cosine theta minus mg equals 0. I'm just gonna go ahead and bring it over also. Do two birds, one stone. And then y sine theta equals mass times, and now what is the formula for acceleration?
V squared over R?
And that's the one that's most appropriate here. What is the other formula? So this is centripetal acceleration because we're traveling in a circle. This is the acceleration based upon a change in direction. So it's v squared over r. What about in terms of, if we wanted to do it in terms of omega instead of v, what would the equation be? Amy, I thought you were about to say it.
I'm not sure, but I'll say it anyway. Would it be R, then the little omega symbol, and then squared over
Yep.
R?
Omega squared, there's something at the end?
Would it be over R, or is that just the way I wrote it down right now?
Possibly just the way you wrote it down. It's omega squared r or r omega squared. I tend to write it at this point, omega squared r. It's possible that what you have right there was omega squared r omega squared over r. It's possible it's written that way, which would just be r squared omega squared over r, and then that would cancel out with one of those after this. Now, why would we use the v one here instead of the omega one? And I suspect at this point, you're probably not comfortable enough to answer that. Does someone want to take a shot at why we want to use v here and not omega? It is problem dependent, and sometimes you go the wrong way. You use v and then later go, man, I wish I'd done omega. Generally, when you're talking about a car, you don't talk about its angular velocity or angular speed as it goes around a curve. For a car, you generally talk about how fast it's going, which is its speed. So v is probably more appropriate for a car going around a curve. If I had something on the end of a string swinging it around, you could go either way on that one. Just that in the lab, omega squared happened to be more convenient because I've done it before, and that's why I shared that with you. When we get into rotational motion in chapter 9, omega is going to pop up more. All right, I have my two equations. In theory, the car has some mass, it has some speed, that angle's often given. And probably R is usually given. And that, in essence, what I'm trying to get to is that Y is something that we want to get rid of. There's more than one way of doing it. It's a math problem. I'm going to do the division thing. I find the simplest for this type of problems when I have something cosine and something sine. So I'm going to take the left side of this equation, y sine theta, and divide by the left side of the other equation. And then, so that's mv squared over r divided by mg. And now the y's go away. You could also solve for y and do substitution. That, in essence, is one extra step, but whatever way your mind is working at the moment. Sine theta divided by cosine theta.
Tangent theta?
That's what I'm looking for. And then over here, what does this simplify into? get back into the fraction mode. I'm dividing one fraction by mg. What do I get? As I wrote it out like this, mv squared over r divided by mg. Does that make it any easier for you?
The m's would cancel out.
They indeed will, because this mv squared over r times 1 over, dividing by a number, same as multiplied by the reciprocal. Mass goes away. G squared over gr. Now, I have not really set up a problem here. This is more of a classic exploration of it. At this point, it depends on what I'm giving you, what I'm asking for. I could go, what is the optimum angle? So if the car's going 50 meters per second and the radius of curvature is 100 meters, what's the optimum angle so that cars can make it around the curve without sliding up or down the ramp? So let's do that. Let's say the car is going 50 meters per second. About 110 miles an hour. Around this frictionless curve. This person's a daredevil. Radius of curvature, we'll make that 100 meters. And what the heck, let's put this on Earth. What is the angle, that ideal angle? Oh. Tangent of theta becomes 50 squared divided by 9.8, and then 100 on the bottom. Somewhere around 2.5. So we're about to reveal what it really is.
2.5513.
As a quick side note, we're not at the end of the problem yet, but what are the units of this 2.5512? Nope, not that complicated. Because it's not officially a speed, it's a ratio of a bunch of stuff. Think about what we found. We found tangent of theta. What are typically the units of the trig functions? Typically no, although if you put radians down, it technically is not incorrect. Just because you can stick radians on whenever you feel like it. Oh, spoiler. There are no units. Trig functions generally produce, it's just a ratio of numbers. All right, so from that, we end up with an angle of
68.59.
I assume degrees.
Yep.
That is a really steep curve there. So we're talking something like this. If you're going 110 miles per hour, that would be an ideal angle right there. If you're going less, bless you, if you're going less than 50 meters per second, what would happen to the car? Assuming that angle.
You go down the hill, or you start going backward.
What do you mean going backwards?
Like, instead of going up the slope, you would instead be going down the slope.
Okay, so as you're going around the curve there, you'd be slowly getting closer to the inside edge. If the angle were greater than that, you'd be heading towards the outside edge. If he traveled at 40 meters per second at that angle, what would he do? So he's driving under that ideal speed for that angle.
You wouldn't stay in the curve, would you?
What would he do?
Slide down.
Yeah, he'd start sliding down. If he traveled more than, say, 60 meters per second,
You give up.
this becomes critical. Usually in a problem like this, I start out with the ideal, so you have some sense of this, of what angle and what speed. So if it's not that ideal combination, then he's going to slide. And if he doesn't slide, that means there's friction involved. Now, whether he wants to slide to the outer part or the inner part determines which way friction will act, and that becomes the critical piece here. So questions on this before we throw friction into it, because the math will get more complicated. I don't think it's as bad as the most complicated projectile motion problem that we did in class. But it is more complicated than most of the stuff that we do. All right, so let's throw friction into it. Tire on asphalt, the coefficient of static friction is 0.9. Now the car is going to be traveling along this road. The car is moving. However, where the tire meets the road, we hope it is not sliding. We will be using static friction because we are going to assume that the tire is not going to slide. So assume that the car is going 50 meters per second. What is the minimum angle? So car will not slide. Because as we drop this thing, the car wants to slide towards the outer edge. But because of friction, it's not going to. However, there is potentially a minimum angle, so that thing's not going to slide. Now, if we get an angle that is less than 0, that means that car's not going to slide no matter what. These equations are going to change slightly. I can keep that because we're just going to tack on, we'll start there. So, which way, since I'm dropping my angle to find a minimum angle, which way is friction going to act on the car?
To the right.
Well, it's going to be either up and to the right or
Oh.
down and to the left.
Okay, sorry.
Up and to the right.
Up and so that way. So the car wants to slide down the ramp.
Correct.
We have taken different curves in our days. This car is cruising around like this. If I drop the angle, the car wants to.
The opposite.
Yeah, the car wants to slide that way. So friction of what hates that.
Oh,
Friction says, no, you're not going to go up. So friction's acting down the ramp. Now we need to bring friction up. Recognize, friction is acting down and to the left. That's where those components are going to be, down and to the left. We could go through and do the math to try to figure out which one's sine, which one's cosine. Or we just take advantage of what we've already done. Friction and normal force are perpendicular to each other. The trig functions will switch. Because y sine theta is the horizontal, friction cosine theta will be the horizontal. Because y cosine theta is the vertical, friction sine theta is the vertical. This works if they're perpendicular. My centripetal force is now a combination of a component of normal force and a component of friction. It is this combination which is the centripetal force. All right, I'm gonna call on two people here just to see how well it's stuck. Brandon, if you don't mind, I want to start with you to give me one of the equations.
So,
And Jacob, I'm gonna do you next.
so F sine theta equals MA,
This one right here.
yeah,
Remember, all the ones that are basically lined up go together.
so the y cosine theta would go that, right?
So y cosine. Did I prematurely erase the other one?
I wish I could tell you what theta, to be honest,
All right, so you got y cosine theta. That really probably should come first because that's in my positive direction right there.
okay. It'd be minus F sine theta equals, no, plus.
Lost one.
What, okay, plus the W,
Y plus w. Feels right?
yeah, it did.
Which is weight going in the positive or negative direction?
Negative.
You sound unsure.
Yeah, negative.
You sound more confident. Yeah. That's why we wrote this over here, to tell you what the positive is. All right. I wasn't sure before when you said plus W, if you put parentheses around that and put a plus W right there, because that actually is legitimate.
Right,
I tend to go ahead and just do the minus sign right there.
okay,
All right, now, equals,
equals.
almost there. You tag team with someone?